Okay, so we'll talk about nuclear energies. Okay. The next few lectures will be on nuclear reactors and stuff like that. How do you get energy from? So let me start off by some basics. I'll give you the big picture, and then we'll learn about details over several lectures. Okay. All right. So let's start off by making a hydrogen atom. Okay. So what you need is to make a hydrogen atom, what you need is a proton and an electron. Okay. I'll just make rough numbers. So we go and buy these two particles at a store. This guy weighs about 2,000 times heavier than this guy. So we'll make up numbers. So let's say this guy is 2,000 units and this guy is 1 unit. So we bought them at the store, and now we'll make a bound state out of it. We'll make a hydrogen atom out of it. A bound state means, see, this electron is bound to the proton. He's going around the proton. He's not running away. Yeah. How much do you think this guy weighs?
1.
This guy is 2,000 units. This guy is 1 unit.
Oh. How much that weight? 2001.
Okay, so that would be the natural answer, 2001. He weighs less than 2001. Okay, so when you make a bound state, the bound state weighs less. All right. Well, what happened to that missing energy? So that missing mass, you guys have seen this equation, E equal to mc squared. Okay. Who came up with that equation? Einstein. Okay. So what this says is, this is the energy equivalence of this mass, and c is the speed of light. Okay. So in making that bound state, that energy was lost. So now if you want to get back, the energy wasn't lost, it was given away to the environment, so to speak. Okay. Now if you want to get the free particle again, you have to put that energy in. Okay. So if you put this energy in, you can ionize this gas. Okay. And the energy needed is to ionize the hydrogen atom. What you need is 13.6 electron volts of energy. If you put in that much energy, then you can ionize this hydrogen atom. Okay. So this atom, its mass is less by this much energy. Did you guys understand that? All right. So if you bind it tighter, if the bound state is tighter, what do you think will happen? Will it weigh less or more? The tighter it's bound, the less it'll weigh. Okay? Everybody understand that concept? Okay. So the tighter you are bound, the less you'll weigh. Okay. Now let's apply this to nuclear energy. So in nuclear energy, you use uranium-235. What does this number 235 mean? What does that mean?
Is that the mass of the...
Maybe you should sit here, so you're in line of sight as well. What does the 235 mean? It's the atomic mass number that tells you the number of protons and neutrons. Okay, so that's what you use in uranium. And again, you'll learn all the details over several lectures. I'm just giving you a brief introduction. Okay? In a nuclear reactor, you use a neutron and shoot it at U-235. This neutron gets absorbed. This nucleus becomes unstable. Uranium-235 is at the fourth one from the last row, the bottom row, left from the left, 92 protons That's the atomic number. Okay? And this is the isotope you use. Okay, so here we go. This thing gets absorbed, and then it breaks up this nucleus. It breaks it up into two smaller nuclei, and then 3 neutrons. All right. So for our purposes, the neutron and the proton weigh the same. Okay? You can think of it like that. And now you shot it with a neutron. How many total neutrons and protons do you have? 235 plus 1, 236. Okay? And when this breaks up, these are neutrons, and these are 2 nuclei, smaller nuclei, 2 smaller pieces. So the number of neutrons and protons is still the same. It's 236. Except that these guys, the total mass of these guys is less than the total mass of these guys. So the number of protons and neutrons are the same, except that these guys weigh less than these guys. How is that possible?
Loss of energy?
How would you weigh less? We just learned that. What happened? What could? Hmm? Okay, so how would this thing weigh less? How could you make it weigh less?
Losing electrons?
If it was more tightly bound. Okay, so in this guy, in these smaller pieces, these neutrons and protons are more tightly bound. Okay, and so on. So when more tightly bound than here. Okay, so that's why these guys weigh less. Okay, and that missing mass is converted to energy. That how much they weigh less, that missing mass is converted to energy. Okay, the delta M just means how much these guys weigh less than this guy. Okay, so whenever energy is released, the products weigh less than the ingredients. Okay, so these guys weigh less than the ingredients. And why do they weigh less? Because these guys are more tightly bound. Okay, well, okay, so to give you, so here's coal. Coal is carbon. When you burn coal, you're combining it with oxygen. Okay, do you get energy when you burn coal? When you burn coal, do you get energy? Yeah, of course. You have all barbecued and you get energy. So that must mean that CO2 weighs less than carbon and oxygen. Okay, that's how you got energy. Except that here's the thing about nuclear energy. When you split one uranium nucleus, the energy you get is 50 million times more than the energy you get when you burn one carbon atom. 50 million times more. Okay? So that's why we like nuclear energy. Now here's the deal. Okay, so again, stop me if you don't understand anything. So I'm giving you a big picture. And next 3-4 weeks, we're just going to talk about the details of this thing. Okay? So the idea is to split the uranium nucleus. Okay? Well, you split a uranium nucleus. Here are 2 pieces. Now these 2 pieces are they are radioactive, and some of these can be radioactive for 25,000 years. Okay? So you just have to maintain that mess. Okay? Now here's the next deal. So you took a neutron and split this nucleus. Now you've got to take one of these neutrons and split a further nucleus. Okay, so you got to take a neutron, this neutron, and split another U-235 nucleus. And keep the reaction going. That's called a chain reaction. Okay, I mean, you just don't want to split one nucleus and stop. Then you want to use this neutron and split another nucleus. use another neutron and split another nucleus. Did you guys understand that? All right. So you're going to take one nucleus, split this uranium-235, and there are the two pieces, and 3 more neutrons, and you want 1 neutron to split another nucleus. Okay? All right, here's the deal. If on the average, less than 1 nucleus causes a further reaction, then that reaction will die off. Okay, the reactor will shut down.
If it's not able to split?
Yeah, so you got, if less than 1
Oh, okay.
neutron does it, okay, then eventually the fire dies out. If more than 1 neutron reacts, splits another nucleus, what you have is an atom bomb. It'll explode. In a nuclear reactor, you want to make sure exactly 1 neutron causes a further reaction. And that reaction will maintain. That'll be a steady state reaction.
So if none split, the reaction dies?
And if less than 1 causes a reaction, the reaction will die. The chain reaction will die. If exactly 1 causes a further reaction, that can be maintained till you run out of fuel. Okay? And if more than 1 causes a further reaction, that's an atom bomb. Okay? So in an atom bomb, that's what you want to do. You're making sure. In a nuclear reactor, you're making sure that 1 neutron causes a further reaction. So there's a whole bunch of things that you do to be able to do that. Okay? All right. Did you guys understand that? So what you want to do is, okay, let's go back to that picture. What you want to do is you want to make sure that more than 1 neutron causes a reaction. Okay? Now, the thing is, okay, so when these neutrons come out, they're going at about 20,000 kilometers a second. That is, this neutron is coming out at a speed where it would go around the Earth in 1 second. Okay, now if the neutron is going that fast, the chance that it'll cause a reaction is small. The probability is less. Now, if you can slow down this neutron to a speed of 2 kilometers a second from here to the speedway, rather than going around the Earth, then the chance that it'll cause a further reaction increases by a factor of 100. Okay? So remember, what is it that you were trying to do? You're trying to make that 1 more neutron cause a reaction, right? So what is your first job? What you want to do is you want to slow down these reactors. These neutrons, so that the chances of them causing a reaction are higher. Okay? Did you guys understand that? That's the job of a moderator in a nuclear reactor. Okay? All right, your goal is to make sure that of those 3 neutrons, 1 cause a reaction, and so to increase the probability of that happening, you have moderators in there. Okay? Okay, so we'll learn about that. All right, so those are the basics. Where did we go? All right, so I'm going to erase this so we understand this. Okay. So you saw that there's energy released, and the energy released in this reaction is 50 million times greater than the energy released here. Okay, so all this is, like I said, this is going at 20,000 kilometers a second. This stuff is hot. What do you do with the heat?
Cool it down,
I'm sorry?
cool it down, and give it this heat.
And the energy is in the form of heat. What do you use this heat? You boil water. Why do you boil water? You produce steam. Why do you produce steam? So you can turn this baby. So there is that wire, there is magnets. You can turn this steam and produce electricity. Yeah, that's what you're doing. So you're converting that heat into electricity. Okay, that's your nuclear reactor. So here we go. Here's another. Since I'm recording this, I got to show you this. Okay. So what you have to do is, so this is slightly different. Anyway, what you need is a wire, and it's either the wire has got to move relative to the magnet, or you can move the magnet. Okay, so so you can see that when the magnet turns relative to the wire, you're producing electricity. Okay. In a dam, the flowing water is turning the magnet. In a windmill, the wind turns the blades, which is turning the magnet. Well, actually, what you're doing is turning the wires like this, okay, in the setup. The magnets are stationary. In a nuclear reactor, the heat released is used to produce steam, which is turning the magnet or the wire, okay? Okay. Okay, so the setup is, and I've shown you this before. So here's the magnet, and what you're turning is this wire inside, okay? The wire is what is turned, okay, in a generator, and that's what I showed you here, okay? And in a nuclear reactor, you use the heat to produce steam, which is used to turn this wire to convert that heat to electricity. In a windmill, the wind turns this wire to produce electricity. In a dam, the flowing water turns this wire. In a coal power plant, how do you produce electricity? Burn coal, the heat is used to produce steam. Steam is turning this wire. Okay? All right, so in a nuclear reactor, about 35% of that heat gets converted to electricity. Okay? Okay, so you guys have a sense for what a nuclear reactor is? By the way, we are going to UF, and we'll see their training nuclear reactor. If we're going this Friday, if you guys want to go, you can still go. You're going, right? You're signed up?
Unfortunately can't, because I have mentorship on Fridays too, so I realized that.
No, I said, so you're not going anymore.
No.
Okay. All right, so, okay, so here, we'll start off with the basics of nuclear physics, and then in the next chapter, we'll talk about nuclear reactors. Okay, okay, so we'll look at the composition and stability of nuclei. So nuclei, here are the nuclei, they're made of protons and neutrons, okay? And binding energy is, when you take ingredients together and make a bound state, when you take neutrons and protons and make a bound state, which is the nucleus. Yep.
Okay, why uranium and not some other radioactive elements?
Okay.
I think plutonium or thorium is used sometimes?
Yeah, they can be used, and there are different reactions. The uranium is most easily fissile, so.
What is the other control? Radium?
No, there are plutonium reactors and stuff like that, and they're used for bombs and all that. But see, plutonium you have to make. Uranium is naturally occurring. So up to 92, they're naturally occurring elements. After 92, they're all man-made. So plutonium is made in a reactor. All the above 92, they're all radioactive. Yeah, they're all radioactive. Above 83, everything is radioactive. Above bismuth and so on, they're all radioactive. Okay. Okay, so we'll talk about binding energy. Like I said, when you make this nucleus, this weighs less, and the difference in mass, that's the binding energy. That tells you how strong it's bound. So that's the amount of energy you would have to put in to split it apart. Okay. There are three kinds of, so if this nucleus is unstable, it will decay radioactively. Okay? And this guy can decay one of three ways: alpha, beta, and gamma decay processes. We'll talk about that. Okay, so everything we're talking about is about this fellow in the next two chapters. And then we'll talk about reactions between neutrons and nuclei. What happens if you hit a neutron to this guy? What kind of reactions can happen? And that's what is used in a nuclear reactor. This neutron, when it gets absorbed by this nucleus, U-235, this becomes unstable and it can split up. Okay? Sometimes it can just spit the neutron back. That's another reaction. But what the reaction that we want is the one where it splits up, where it's fissioning. Okay? All right. So here's an atom. Yep. There's the nucleus. There's the electron cloud. So the electron is like a cloud out there. Okay. The thing is, the size of this atom is 10 to the minus 10 meters, and the size of the nucleus is 10 minus 15 meters. Okay, so this drawing is not to scale. The atom is 100,000 times bigger than this guy. So if the atom were as big as a football stadium, the nucleus would be the size of a marble. All this electron clouds weigh nothing compared to this. So all of the mass of the atom is in the nucleus, essentially. Okay? So the size of the atom is 100,000 times the size of the nucleus. While the nucleus is tiny, almost all the mass of the atom resides in the nucleus. Okay? Electrons have negligible mass. Okay, so now in the next two chapters, what we're doing is we're going to mess with this fellow. Okay? And we're going to try and extract energy from it. Okay? So this is just term. A nuclide is a nucleus with a specific number of neutrons and a number of protons. Okay, so so they don't give you the mass number there. The number on the red at the bottom is the weight, and that's the average weight of all the isotopes together. Okay, the number in the blue on the top right of each element, that's the number of protons each element has. Okay, so again, coming back to uranium 92, that tells you the uranium has 92 protons. The number of protons identifies it's the social security number of an element. Okay? So that's the number of protons and electrons it has. Okay? That's called the atomic number. Okay? So that number of protons is Z. So protons and neutrons together are called nucleons. And protons and neutrons weigh the same, and they weigh about 2,000 times heavier than the electrons. Okay, so here is the element symbol. Okay, so we'll do so here's an example. Carbon, that's the symbol for the element. 12 tells you the number of protons and neutrons, and this number tells you the protons. Okay, so here's carbon 12. Carbon 12, it has 6 protons. All carbon have 6 protons. And this 12 tells you that it has 6 protons and 6 neutrons. Okay, here's an isotope of carbon. Okay, what does this tell you? So this is carbon. And why is this carbon? Because it has 6 protons. Again, the number of protons identifies the element. So now what is this number telling you? So 14 minus 6, 8 neutrons. Okay, 12 minus 6, so this number is telling you that it has 6 neutrons. And this is telling you it has 8 neutrons. Okay. Now the chemical properties of these, again, so I'll draw. Five, 6, and then it has a bunch of neutrons. I won't draw the neutrons. Okay. So here's carbon. It has 2 electrons here, 4 electrons here. See, all the chemical properties of carbon are determined by these 4 electrons. How many electrons you have in this outermost shell? Yeah, so all the chemical properties, it's got nothing to do with the nucleus. Okay, so carbon 14, it has 8 neutrons. It has 2 more neutrons there, but it's chemically identical to the carbon 12. Okay, so chemically these 2 guys are the same. This guy is just heavier. Okay, this guy is called an isotope. Okay, when the number of neutrons are different, those guys are isotopes, but chemically they're identical. Okay, this guy is just heavier than him. Okay, he's about 20% heavier than him. Okay. And because he has more neutrons, this nucleus is unstable and he will decay radioactively. Okay? So carbon 14 will decay radioactively. Have you guys heard of half-life? Mm-hmm. What does half-life mean?
How long it takes for it? Just how long it takes for it to decay, half of its percent.
Very good. Okay. So the carbon 14 half-life is 6,000 years. It's 5,740 years. We'll say it's 6,000 years, just to keep it simple. Okay, it's 6,000 years. What that says is, in 6,000 years, the probability of a nucleus, a carbon 14 nucleus decaying is half. All right. Why does it matter? Okay. So let's say this is a tree, or this is an animal that lived. Okay, so let's say this is an animal that's alive today. Okay, and we know from its body mass how many carbon atoms it has. Okay, so and the ratio of carbon 14 to carbon 12 is known. Okay, in living matters, it's known. It's okay. So let's say this animal is weighs how much ever, and it has 1,000 carbon 14 atoms when it's alive, and then it dies today.
Okay, I found this on the web. For this is an animal. That's a lot, and we know from its body mass how many garden atoms has the ratio of carbon.
Okay, so this animal dies today. 6,000 years from now, how many carbon 14 atoms will it have? 500. 12,000 years after it dies? 250. So you see, all you have to do is count the number of carbon 14 left, and you can tell how long ago it died. That's carbon dating. That's radioactive dating. Okay. Did you guys understand that? So we use it for that kind of stuff. What if you want to date something that is not thousands of years old, but hundreds of thousands of years old. What do you have to do? How do we know that the Earth is 5 billion years old?
Wouldn't you do the same thing?
Huh?
Wouldn't you do the same thing?
Yeah, but in a few years, all the carbon will be all gone. So all you have to do is find something, some radioactive clock whose half-life is a lot longer, that's all.
I was thinking,
So-
because sometimes they like measure like oxygen level with the ice thing, but I don't know if that would work.
What's that?
Sometimes like in the ice caps, they like go and get.
Right, ice cores,
Yeah,
yep.
but I don't think that would work.
Yeah, so
I wasn't, did they how old it is?
anyway, all you have to do is find a clock that's much longer. So uranium clocks are billions of years half-life. Okay, so there are half-lives with all kinds of different ages. Okay, so you just have to find the appropriate clock. But that's the idea. Okay. All right. So this number tells you the number of neutrons and protons. This number tells you the number of protons, and that's the symbol for elements. Okay. So this number is called the mass number. Okay. Now on the periodic table, they don't have the mass number. Okay. Masses of elements are given as masses of the neutral atoms. So those things are not the mass number, but the masses of those elements, those red numbers. Okay, so for instance, lithium is 6.941. Okay, lithium on the top left, so that's the average mass of all the isotopes of lithium, and we'll come to that. Okay, so the mass of carbon-12 is exactly 12 atomic units. That's defined to be. Okay, so carbon-12 is defined to be 12 atomic units. Okay, and so if you look at nitrogen on the top row, top right, nitrogen is N7. It's 14.0067. Okay, so if carbon-12 weighs 12 units, nitrogen 7, along with all its isotopes, the average weight is 14.0067. Okay, that's what that means. Okay. All right, so here are isotopes. What are isotopes? Isotopes are just cousins of the same. Okay, so here's oxygen 16, oxygen 17, and oxygen 18. Oxygen has 8 protons, so this guy has 8 protons and 8 neutrons. Oxygen 17 has 8 protons and 9 neutrons. And this guy has 8 protons and 10 neutrons. Okay, so this guy is just heavier than this guy. Okay, so all the isotopes have different weights, but their chemical properties are the same because the chemical properties are determined by the outermost electrons. Okay, and the number of electrons are the same. Okay, these guys are called the valence electrons. How many valence electrons are there? 1, 2, 3, 4, 5, 6 valence electrons. Okay, what does an atom try to do in all the chemical reactions in general? It's trying to either fill this valence shell, 8 is a full valence shell, or empty a valence shell. What's easy for oxygen to do?
Bind to itself?
Huh?
To bind to itself?
To go and find 2 electrons. Okay, so it can have a full valence shell. Okay, that's all it does. So all the guys on the right have almost full valence shell. The guys on the left, hydrogen has 1 electron in its valence shell. Okay, so hydrogen is willing to share its electron. Okay, so if you take oxygen and 2 hydrogens, okay, what is happening? This hydrogen is sharing its electron with this oxygen, This hydrogen is sharing its electron with its oxygen. And then it has a full valence shell. And this is water, one of the most common compounds. Okay? So in all the chemical reactions, all it's trying to do is get a full valence shell. Okay, so these are isotopes. Isotopes way different because the number of neutrons is different. Okay? But their chemical properties are the same. And so a nuclide is identified by this, where E is the name of the element. This is the number of neutrons and protons. Isotopes of an element have identical chemical properties. Okay? They just have different number of neutrons. Okay? So this guy has 8 protons and 8 neutrons, that's 16. 8 protons and 9 neutrons, that adds up to 17. 8 protons and 10 neutrons, that adds up to 18. The number of electrons is the same as the number of protons. Okay? Here are isotopes of carbon. Carbon-12 is 6 protons and 6 neutrons. Carbon-13 is 6 protons and 7 neutrons. Carbon-14 is 6 protons and 8 neutrons. This guy is radioactive and has a half-life of 6,000 years. Okay? And we use this guy for carbon dating. Okay? So actually, there are several other carbon isotopes. This is the number of neutrons. There's a carbon-9 with 3 neutrons, and so on. And you see, its half-life is 127 milliseconds. If you make this in a lab, within 100 milliseconds, within a tenth of a millisecond, it'll decay away. Okay, so this tells you the half-life. Okay, so the only stable isotopes are 12 and 13, and their half-life is infinite. Okay, carbon-14, you see there's its half-life, 5,730 years. So this tells you the half-lives of all those guys. Okay, you see, so the further away the neutron number is from the proton, the faster it radioactively decays. Okay? Nuclear stability. What this tells you is what kind of nucleus are stable. Okay. This is the proton numbers in the nucleus. This is the neutron number in the nucleus. So what this graph is telling you is, so if you make a nucleus in this blue region, that's stable. The light blue you can make, and they'll radioactively decay. And the ones here, you can't make them. Okay? All right, so the dark blue are the stable, the light blue are unstable, and they'll decay, and these guys you can't make. Okay, so what this graph is telling you is, when you're making small nuclei, the number of neutrons and protons are the same, and as you make bigger and bigger nuclei, so if you try and make something with 80 protons, what you need is almost 100 neutrons to make that nucleus. As you make heavier nuclei, you need more and more neutrons. Why do you need more and more neutrons? Why do you think you need more and more neutrons? See, these protons, they're positively charged, they repel each other, they don't like each other. So to keep them apart, you put more neutrons in between. Yeah. So as you get heavier, as the nuclei get heavier, you need more protons. That's what this graph is showing you. Okay. This is a Serge plot of stable nuclei. Nuclei in the dark blue area are stable, while the ones in the light blue are unstable and they'll radioactively decay. Okay. So nuclei with N and Z that are not in the band can neither be made in a laboratory nor do they exist in nature. So you can't make a nuclei like that. Yeah. All right. Heavy nuclei with a large number of protons require n greater than z to keep the protons apart to be stable. Okay, now you'll understand this thing. Okay, so when you split a uranium-235 nucleus, uranium-235 is a large nucleus. It has 92 protons, U90, okay, so 92 protons. It's a large nucleus and it needs a lot of neutrons. Okay, do you see it has 92 protons, and how much is 235 minus 100 is 135, and then plus 8, 143 neutrons. Yeah, it has 143 neutrons. And when you split it, you made it into smaller nuclei. You don't need as many neutrons in these nuclei, and so that's why you spit out 3 neutrons. Okay. All right. So, yeah. So nuclear stability. Okay. So those guys are stable nuclei. Okay. Most stable nucleides. If a nucleus is stable, it has both even number of protons and even number of neutrons. Okay. Only 4 stable nucleides. So this is just giving you, data. Okay. Only 4 stable nucleides have odd Z and odd N. Okay. These guys are odd nucleides. Okay. So this is one proton and 1 neutron, 3 protons and 3 neutrons. So okay, and 5 protons and 5 neutrons, and 7 protons and 7 neutrons. These guys are the only ones that are stable. All right, so this is the important graph. Okay, so let's make sure we understand this. And okay, so let's, I'll start off with a simple example. So this is, what is this fellow?
Hydrogen.
This is hydrogen. We'll make a isotope of hydrogen called something called deuterium. You guys have heard of heavy water? The symbol for this is D, this is H. Okay. Heavy water is just in the nucleus, there's a proton and a neutron. And since it has got only 1 proton, this is also an isotope of hydrogen. Okay, this guy is just heavier cousin. Okay. Okay. Now, I said the mass of the proton is, if the mass of the electron is 1, the mass of this guy is about 2,000 units. Okay. How much does this guy weigh? Proton and neutron weigh the same. 4,000. Okay. Except that this guy is bound, so he weighs less than 4,000. Right? So let's say he weighs, I'm just making up numbers, 3,800. Okay? So this guy weighs 3,800 units. So now each proton and neutron is weighing about 19,900 units. Did you guys understand that? So when the nucleon was in a bound state, now it weighs less. Okay? And the tighter it's bound, the less it'll weigh. Did you guys understand that? All right. So that's what this graph is telling you. Okay, so if this is the mass of a free proton, if you put a proton in this nucleus in krypton, okay, that's its mass. If this is 2,000, it's less than 2,000. Okay? In uranium, it's weighing that much. Okay? And so here's how you get nuclear energy. When you split this nucleus into smaller pieces, each of those nucleons weigh less in the smaller pieces because they're more tightly bound, like we talked about, and that energy is released, that missing mass is released. Okay? Again, when do you release nuclear energy? So when the products weigh less than the ingredients. You took a neutron and you split this guy into two pieces, and the reason these guys weigh less is because these guys are more tightly bound. Okay? All the neutrons and protons are more tightly bound here, and they weigh less, and that missing mass is what's converted to energy. Okay? And what's the lure of nuclear energy? Why are we so gung-ho about nuclear energy?
It's clean.
I'm sorry?
It's cleaner.
It's clean, and a lot of it is released. Okay? For every uranium nucleus you split, you're getting 50 million times more energy than every time you burn carbon. Every time you burn one carbon atom. Okay? And then on top of that, you're not releasing any CO2. Okay? So nuclear energy is great. Okay, so this is a binding energy curve. It tells you how much a proton weighs in every element. This graph costs millions and millions of dollars to produce. Okay? So what this is also telling you is the bottom of the graph is for iron. Okay, in iron, the nucleons are most tightly bound. You can't get nuclear energy out of irons. Okay. So there's two ways of getting nuclear energy. You can take a heavy nucleus, split it into smaller pieces, and those guys are more tightly bound, you can get energy. Or you can start off with protons and make these nuclei, and you can get energy. This is called fusion. When you start with protons and make heavier nuclei, that is called fusion. And when you take a heavy nucleus and split it and go that way, that is called fission. This is what we do in a reactor. This is how the sun produces energy. Okay? So the sun that's what this graph is telling you. Nuclear energy can be obtained by fusion or fission. Nuclear energy can be obtained by fusion. You can go up to here, up to iron, and get nuclear energy, or by fission, splitting a heavier nucleus. Okay? So fusion is going this way, and fission is going this way. Okay. Fusion is the process of combining smaller nuclei to form larger nuclei up to iron. Fission is the process of splitting larger nuclei into smaller ones to get energy. Okay, there are four forces in nature: the strong force, the electromagnetic force, weak force, and gravitational force. The strong force, if this gives you the relative strengths. Okay. If the strong force is 1 unit strong, the electromagnetic force is 100 times weaker. The weak force is actually you can roughly say 1,000,000 times weaker. And the gravitational force is tiny. It's 1,000 trillion times weaker. Okay. This gives you the range and so on. Okay. So here's what this thing is good for. Okay. So the range is a femtometer. This is a femtometer. Okay. So here's a nucleus. So here are two protons. They're positively charged. What do two protons do? What do two like charges do?
Repel each other.
They repel each other. Okay? And the electromagnetic force is very strong. So they would repel each other with quite a strong force. So let's come to the nucleus. Here's protons that are tightly packed. So why aren't they flying apart? Hmm?
Because of the neutron.
The neutrons are neutral. They don't do nothing.
Doesn't it, like, go in between the protons, so it doesn't
Yeah, well, I mean, if I and him don't like each other, the fact that she's come in between doesn't change that. We're still repelling each other.
the electrons then?
The electrons they weigh nothing.
Because
The,
the bond?
yeah, but okay, so the electrons are outside. Okay, this guy is attracting him. That's still not preventing these two guys from repelling each other. And the closer you are, the stronger the repulsion. So the fact that these are not flying apart, there must be a stronger force between them. And that is the strong force. This strong force is 100 times stronger than this guy. That's what's binding him. Except that here's the thing. For this strong force to come in play, the protons have to be that close together. Okay, they have to be within 10 to the 15 meters. And that's why all these nuclei are tiny. That's what we saw in the first page. Okay, so whenever you put together an atom, that nucleus is tiny, the size of the nucleus is that, because then you have to bring all the protons and neutrons close enough so the strong force can keep them bound. Okay? So the nuclei of all those elements are tiny, roughly that size. Okay? So you can have the protons close enough where the strong force overwhelms the electrostatic repulsive force. Okay? All right, so this strong force, which is 100 times stronger than the repulsive force, is keeping the protons together. So here's Einstein's relationship. It tells you the energy equivalence of mass. If you could convert this mass to all its energy, so that tells you there's a lot of energy in mass. Okay, so for instance, I've mentioned this before. You go to the parking lot, take any car in the parking lot, and if you could convert all of that into energy, you could run our country for an entire year. That's how much energy is contained. Okay? So that's not easy to do. Okay? So c is the speed of light. Okay? So if all of the mass of a small car could be converted to electricity, one could satisfy the energy needs of the U.S. for an entire year. Okay. Okay, so this tells you the binding energy. The more strongly a nucleus is bound, the less it weighs. Okay. And this tells you, and the harder it is to pull apart. Okay. So how do we get fission energy? Okay, so you're taking a nucleus and splitting it into smaller pieces, and these pieces are more tightly bound, so that's why we are releasing energy. Okay. They're more tightly bound and they weigh less, and so that missing mass is released as energy. Okay. You don't have to remember these formulas. This just tells you. Okay, so you put together these nuclei, this nucleus. How did you put together this nucleus? You used protons and neutrons. Okay, so this is the mass of all the neutrons. This is the mass of all the free protons. And this is the mass of the nucleus. Because it's a bound state, this weighs less than this guy. And the more tightly this is bound, the greater the difference, and that's the binding energy. Okay? This is the amount of energy you would need to split it all into all the protons and neutrons. Okay? So that's the binding energy. It tells you how tightly the nucleus is bound. All right, so the less the mass of this guy, the more tightly it's bound. Okay, so this shows you, okay, so what this is showing you is various nuclides, various nuclei. See, the mass number is the same, 49. That's the number of protons and neutrons is the same. The number of protons is different, and so that's why the elements are different. Okay, this tells you the number of neutrons and the number of protons. Okay, so you're putting together these nuclei, and here is the mass of these nuclei. Okay, you see this mass changes. Okay, this guy, 48.99478, this is the least massive of these nuclei, and it's stable. The other guys have greater masses, and they're unstable, and they decay. So they decay via this thing. And you see the half-life is 57.5 minutes. The more unstable it is, the faster it decays. Okay. This guy, okay, so when you're a small nucleus, what you want is the number of neutrons to be roughly equal to the number of protons. Okay. In this guy, you see the difference is large, and so it's unstable. Okay, and its mass is greater, 48.95. See, 48.94 is the mass of this stable guy. And well, okay, so also with this number of protons, you need more neutrons to keep the protons apart. So here, 24 and 25, this is 48.95. This is, the mass is greater than that, and it's unstable. The half-life is 15 minutes, an hour. So the stable nuclei are the most tightly bound nuclei, okay? Okay, so if something is unstable, if a nucleus is unstable, it can decay one of three ways, okay? So that's radioactivity. If a nucleus is unstable, it decays. Why does it decay? Why does a nucleus decay? I'm sorry? It's unstable, so why does it decay? It wants to become stable. So it wants to become something that's stable. Okay? So here's a nucleus. So this happens in heavy nuclei. It'll split out an alpha particle. An alpha particle is the nucleus of a helium nucleus, helium atom. Okay? It will spit out 2 protons and 2 neutrons, which is an alpha particle, and hopefully it'll become more stable. So it went from here to here in the hopes of becoming stable. A beta decay is it splits out an electron. In a beta decay, if it spits out an electron, what happens is a neutron got converted to a proton. If it splits out an anti-electron, then a proton becomes a neutron. Okay, so it tries to become stable by either converting a neutron to a proton or a proton to a neutron inside the nucleus. Yeah. A gamma decay is just this nucleus is excited, is in an excited state after one of these decays, and it emits a photon to become de-excited. Okay, so those are the 3 kinds of radioactive decays that can happen. Okay, and what is happening as unstable nucleus is trying to become a stable nucleus by this radioactive decay. Okay. If a nucleus is unstable, it will decay via radioactivity and move towards stability. Okay. All elements beyond bismuth, atomic number 83 in the periodic table are radioactive. So all those elements are radioactive. Okay. They're naturally occurring, but they're all radioactive. So that guy's radioactive, all those guys are radioactive. Oops, these. Yeah. All these guys are man-made. The ones that are dark, they're all naturally occurring. So up to 92, you have those are naturally occurring elements. Okay? Beyond 93, they're all made in labs. So when nuclei decay, three distinct types of radiations are observed: alpha particle, beta particle, and gamma particle. Okay? All right, we'll stop here.